The unique Mediterranean climate has provided the basis for food and economic growth for thousands of years. Groundwater plays a decisive role for the supply of water. It is almost exclusively stored in karst aquifers surrounding the Mediterranean Sea.
We have counted 40 karst aquifers in southern Italy. In this area, there are conditions that favor a high infiltration groundwater recharge and relevant groundwater circulation, which is basically oriented toward very huge basalt springs.
Karst features, such as sinkholes and conduits, result from the dissolution of soluble rock like limestone by circulating groundwater. Groundwater flow in karstified aquifers is very complex. While water rushes through fractures, conduits and even caves, it moves much slower through the surrounding rock matrix. As a result, karst conduit networks quickly drain new recharge. A lower proportion of groundwater is stored over a long period of time. Karst aquifers supply approximately 10% of the world's population with fresh water. But especially in the Mediterranean area, they are vulnerable with respect to quantity and quality.
Drinking water supply to Montpellier metropole relies mostly on groundwater resources, especially from karst aquifers. Climate change will impact natural infiltration. We expect a decrease of about 25% in 2060.
As the climate changes and demand rises with growing populations, uncontrolled abstractions could have serious consequences for water supply. The international research project Medwater studies the behavior of karst aquifers, investigates influences and threats on karst groundwater, and develops strategies and tools for their sustainable management. The project studies the highly karstified Western Mountain Aquifer in Israel and the Palestinian territories that provides approximately 20% of fresh water for the area. The foundation of our work, data, is not always accessible. But innovative methods, such as remote sensing, can provide or complement missing data. Here, we downscaled satellite data to measure soil moisture dynamics, which supports hydrogeological modeling and the assessment of ecosystem services. The most important input factor is groundwater recharge, which infiltrates in the eastern mountainous area. The recharge zone not only dictates the availability of groundwater for humans, it also plays an important role for ecosystem services. For the aquifer, the recharge zone provides 70% of flood regulation, 80% of soil erosion regulation, and 75% of water quality regulation. Most groundwater recharge in the Mediterranean occurs during the period October to March. The rainy season is expected to be seriously affected by climate change. Our projections until 2070 predict for the aquifer recharge zone a temperature increase by up to 2.2 degrees centigrade. Precipitation may decrease even by 58%. How this affects the total volume of groundwater recharge is a complex question.
The decrease in recharge caused not only by decrease in total rainfall, but also by change in rain distribution and increase in evaporation. Quantitative assessment of this phenomenon done by Medwater enable us to make more correct prognosis of future recharge trends.
One suitable method to calculate event-based recharge is the Soil and Water Assessment Tool. With model projections until 2070, we expect annual groundwater recharge of the Western Mountain Aquifer to decrease by circa 20%. To visualize flow paths, we used the stochastic karst simulator. The tool generates a probability map of karst conduits, employing information on a geological, landscape and paleoclimatic history over millions of years. To predict changes in groundwater availability, we developed a complex groundwater model with a modeling code hydrogeosphere, which is capable of simulating the complex dual flow type system of karst aquifers. Step by step, we developed a better understanding of how karst aquifers function. Now, the goal is to maintain safe groundwater levels that can supply populations in the long term. For the Western Mountain Aquifer, these are visualized by a red line. Overexploitation would lead to irreversible salinization of the aquifer. With scenario analyses, we found that resource-intensive pumping may lead to a rapid 2-meter groundwater level decline over the next 5 years, followed by a further drop of 3 meters by 2040. Not all abstracted groundwater serves to provide local populations, though. Much of the water used for agriculture is used for the irrigation of crops that are exported to other countries. Calculations for 2005 showed that 1,800 million cubic meters surface and groundwater is used for Israel's food production. 11% comprises water for export. Our results are incorporated into user-friendly products. A decision support system processes the results of the groundwater model, recharge estimates, climate projections, and scenario analyses. It helps to simulate the aquifer response to changed input values and pumping rates. Results from Israel are transferred to similar aquifers in Italy and France, and eventually can be applied in the whole Mediterranean region, where populations keep growing rapidly. While abstractions are likely to increase, natural recharge will considerably decrease at the same time. By the end of the century, 15% of karst aquifers with Mediterranean climate will have moved into more extreme climatic zones, that is, steppes or deserts. To face these future challenges, Medwater has created new opportunities to manage karst aquifers in a smart and sustainable way, giving decision makers the tools to ensure water supply for humans as well as ecosystems.